All right, so the plan for today, I want to dive very deep into your lab number 1 solution. Now that you guys already try it for M1, M2, and also fix the problem for M0, I would like to talk about certain things I heard from office hour and also from the TA who attended the scheduled lab session. I want to just highlight them, but there will be certain aspects I think it's also worth our attention during the lecture time just to make sure everybody can be aware, and then when you study later for your programming tests and the written tests, you can also make sure you have no problem with them. All right. So today I want to talk about number 1, your lab 1 solution. Not really every line. You guys already got all the files from the solution as a zip file. You should really take a look, but I'll highlight the ones that are trickier to really identify. I'll also try to do a little bit demo. It's really not necessary, but I can do a little bit demo just to show to you when you actually want to reproduce what I do in class today. You also really, of course, you got to get yourself very familiar with the TRA Plus, which will be necessary for your programming test. And your lab number 2 has been released, and that one there is going to be very relevant to your upcoming programming test 1. All right? So for the guide for the actual programming test, I'll try to release it maybe early next week. So you can also take a look. And also, we also got your mock-up test at some point. I'll also mention the details a little bit later. All right, TA contact information, office hour, just as usual. Nothing changed. All right, guys, any question in general? All right, so let's now do a very quick recap about last time, and then I'll dive deep into lab number 1 solution. I'll do lab 1 solution first. That one might take a big chunk of today's time, but as I said, it's really important for your learning. I'll do that properly. And after that, we can take a very short break. And then after break, I will talk about your lab number 2. Just give you some very quick guidance about how you should really approach it. So you can also prepare your programming test number 1 at the same time. And as for the math review, we only got just a few exercises. I kind of promised you guys I'm going to prepare some nested quantification. I did. I do have the example here, but we'll see if we can get there. If no, then definitely we'll do that on Thursday. That can also help you understand a little bit more about the basic quantification. All right, so that's the plan. We'll see how far we can go. But interrupt me in the middle anytime I go too fast. All right, so last time we basically continued with the review on the math, especially about quantification, right? We talked about you should really know about the ASCII syntax that will be definitely necessary for your programming tests and labs. And these are the things you should really get yourself familiar. Not necessarily everything we kind of mentioned to you explicitly will be something you will need. You might need something additional, right? So you really want to be more responsible for what you need in the actual labs and also the test. And for the exam, also for the lectures, it will be more on the math syntax, right? Which we also spoke about. The example I'm going to go over with you about nested quantification, it will be also on the math syntax on paper, right? That's something we'll do. All right, quantification, you guys got to really make sure you understand, number 1, the syntax, right? For all exist, and also the range over here, universe of disclosure, and also the properties over here, right? And also in the case of for all, it's going to be an implication, and for existential quantification, it's going to be a conjunction, right? You got to know the syntax, you got to know the meaning, and also you got to go for the examples that we went through in the class. And also we talk about the special cases, especially if the range predicate here happen to be false. Then we know that in this case, the for all will just be trivially true, as opposed to in the existential case, if this range predicate here happen to be false because we got conjunction. So it's going to be trivially false, right? And also try to make some connection to programming. You can also go over that. And we talk about nested quantification, right? That's only the idea. I do have some concrete example, but it's already on the template page for the notes. For those, if we cannot really get there today, you can feel free to take a look and give it a try. Just determine it's either true or false. If you believe the nested quantification is actually true, how would you prove it? If you believe that's false, how would you disprove it? So the strategies that we spoke about last time will also apply. You want to be very clear about what's going on. But that's something I will hint to you as well. Right? Anyway, so once you see the example either today or before Thursday, you gotta understand. Right? All right, so these are just some basic examples about quantification, right? You guys seem to be quite comfortable with it. You just got to be careful whenever you want to justify, right? Either justify informally or justify formally. And we do have the formal, like a proof strategy you can follow. All right, so these are the proof strategy. I'm not going to repeat. So, but for all, you got basically either to prove or disapprove. And for existential quantification, it's either to prove or disprove. And we even actually highlighted that the proof strategies somehow are quite symmetric for the two quantification. That's something you also want to look into, when you study for the strategies. And then we also did some example here, basic one, but that should be enough to illustrate the idea. So for nested quantification, once we get there, we will follow some very consistent strategy. May not be exactly like this, but along the same principle. Right? That's something we can also try. But you guys should really try to come up with more example on your own, form some study group and see how things should be understood. Or just Google for nested quantification. There are tons of examples on the web. Good. All right, we're talking about general form. All right, that's basically what you guys learned maybe from 1090. I kind of explained that, so these are just equivalent to the forms that we are talking about in this course and 3342. The reason that we are having either implication or conjunction for different quantification is because the tool that we're using for better processing or more efficient processing, they kind of a restricted way you have to write the quantification. But mathematically wise, math-wise, they're really equivalent, right? So there's no contradiction here. Right, so here we'll talk about the two axioms to really convert between one quantification to another, right? And we use that to show you, that's a final thing, we show you how you can do the so-called equational style of proof, right? So this will be the style of proof that we're gonna get adapted to in this course. We don't do sequence proof anymore in this course, like what we did in 3342. But again, don't really think there's it's a different system, yes, but the theory or theories or theorems behind are really the same. It's just a different way to present the formal arguments, right? Just you want to get used to this equational style. Between the steps, basically, you just have to put some justification, like an inference rule in the case of the sequence calculus, sequence proof. All right. All right, guys, any question from last time? All right, that's good. So, as I said, I would like to now dive very deep into your lab number 1 solution, right? I'm going to go over with you. If you had a chance to already look at them, very good. If no, maybe after today, you really want to maybe at least look at the parts I kind of went over with you in the class. But there will be some minor stuff which I think you can also go through without my help, right? Of course, drop by the office hour if you got any trouble. All right. So just go to the e-class page. I'm not going to show you that. Just go there and you can download the Lab 1 solution. It's actually going to be a zip file, right, as I mentioned earlier. So the zip file, don't import the zip file into TLA Plus directly. That's not the way to go, right? You basically just got a zip file, unzip it, you will get multiple .tla files. There's also a README file to actually give you a little bit quick guidance about how you're supposed to read into the solution. But I'm going to mention them to you as well. All right, so let's now dive deep into Lab 1 solution. Okay, so there are 3 aspects I would like to go over today, for sure. Okay, so number 1, it's about we want to do model checking. So, and we talk about reachability graph. In order for your model checking to really terminate, at least, the reachability graph over here should be finite, right? That's something we spoke about, in the introduction part of the course, right? Finite reachability graph is really for the checking, model checking, to terminate. If it is infinite or it keep growing, there's no way for the model checking to really terminate, right? It's very important. And in your Lab 1 tutorial video, I rewatched them. So now I think that covered really everything you really need to know about the tool. Right? So we kind of did some pattern over here. Let me just tell you this, and then we'll dive into detail. So what you learned in the tutorial video was something like this, right? So you say something like you have some bound variable, and then maybe initialize that to be 0, let's say, like a C style. And then you say while the bound is less than 0. And then, of course, I'll just put it in comments. You kind of do some selection about the different events, right? Selection of events. Of course, you got to make sure you say the bound should be incremented. I'll just say plus plus over here, right? That's the pattern you learn in the tutorial video. And the reason that we have a bound over here is to make sure the number of events that's going to be in a trace that we consider is bounded. So we make sure you really got bounded model checking. Basically, make sure you guarantee to terminates. So this is to make sure we got bounded checking. In some ways, it's a very explicit approach to make sure the length of the trace you're considering is kind of limited, right? Can be 1, can be 2, can be 3, or all the way up to 10, right? We'll talk about also how you can figure out the total number of possibility in general, right? It's all workable. So this is good, nothing wrong with it. Okay, all good for this one here. But in the solution files, in all the files, actually, I kind of show you another way to really do this one. You still need a while loop, but what you will see is something that might seem very weird in the beginning. Since we said we want to do bounded model checking, so what you will see is over there, I'll say versus. What you'll see there's no bound anymore. All right, there's no like an explicit variable to restrict the length of the traces. No. What you will see is you got while and then true. I'm pretty sure you guys know while true, infinite loop. All right, this is important. And then somehow this is the selection you will see, right? I'm going to let you, I may not actually dive into the exact coding detail, but you can take a look, when you see the solution. And it is important to know the following, right? So whenever you want to use this pattern here, which will work if you design the guards of your events carefully. All right, that's a very big assumption, I know, right? Of course, if you didn't design your event guards carefully, you might just write into memory, out of memory error, because your reachability graph is actually infinite. All right, so let me write down the assumption here, and then we're going to talk about it as we go through one example. So this point number 1 is pretty important, right? So here we can use the while true with a very big assumption. Okay, the assumption is assuming that the guards of your events, are such that the reachability graph remains finite. And I'll put a little bit more details here. Remains finite. That's the first thing you want to really understand. Changing this to true doesn't necessarily mean your reachability graph is going to be infinite. Not necessarily. Okay? Reachability graph remains finite. And the way we're going to judge is by making sure, i.e., there'll be no events transitions. For example, let's say in your M0, you got ML out, ML in, these two events. So the guards for these two events should be designed in such a way that there is no way for the event to always be enabled and reach out to new states. So your reachability graph will just keep growing. This should not be allowed to happen. Okay? So no event transition that are always enabled to reach to new states. All right, I'll visualize this a little bit just to give you a little bit more intuition. But this paragraph here is actually quite important. There's no event transition that are always enabled to reach new states. So what you really want to avoid is as follows. As the tool is trying to build a reachability graph, for example, let's say if we got init over here, if somehow you didn't really design your transition the events or transitions or procedure properly with the guards. So for example, you might say after the initial states, there is always a way, for example, for some event, let's say E, to really keep growing. And every time it goes, it's actually going to a new state and etc. You can see the number of nodes will simply just grow without going back to some other existing node, in which case we might have a loop. So the reason that the reachability graph remains finite is because it contains cycle. Right? You guys learned in 3101. If you got a graph over there, if you've got a cycle, that means the edge will go back to itself. Right? I mean for the nodes. Okay, I'll give you some quick insight, visual. Okay, so here, so basically remains finite by having cycles. And we'll talk about cycles and also infinite number of paths, right? Don't get me wrong. When we talk about the number of nodes in the graph, it must be finite. However, the number of possible paths you might go for your system might be infinite. All right, that's something we'll definitely get into very deep when we talk about temporal logic, right? I just want to mention that without writing down. All right, by having cycles, right? This is a very important point over here. So think about this first case over here is like an infinite number of states or nodes in the graph. Because your graph can simply just keep growing, right? Keep growing to new states, keep growing without ever being restricted, right? That's something you definitely don't want to run into. If you run into it, your model checking does not terminate. On the other hand, what we want to see, when I say such that, what we want to see instead is to see somehow the states will actually go back to itself or to other existing states. Something like this. So here, this will be the good case. So let's say we got inits, and maybe we got a certain number of states in the beginning, in the middle. And now, if we try to do some event E, it might either go back to itself, it does not reach to a new, like a new state, or it might simply go back to some existing states, right? For example, something like that, either way. That's going to make sure, even though you got so many different possible paths that might exist in the graph, but the graph is still finite, okay, for you to model check. Finite number of states, however, infinite number of possible paths. Having infinite number of possible paths is not a big issue for model checker because they will actually find a pattern and then check it. We don't need to know too many details about how exactly they check it, but once we get to the temporal logic, we have to somehow look at the graph manually ourselves. I'll give you more insight once we get there. But for now, you don't need to, all right? So here, the infinite number, so this will not cause model checking not to terminate. All right. Well, just for the first point, I haven't shown you any detail just yet, but it's very important to clarify conceptually. Bottom line, what you guys have to do is, this is something you already learned from the tutorial video. Make sure to review it, understand it. Number two, when you see the solution, also make sure you understand this pattern here. Maybe in the programming test or in the written test, I might just ask you a question about either pattern. All right. That's why I want to spend enough time with you in the class. All right, that's point number one. And point number two is about, this might be the most commonly asked question, which I can appreciate the confusion. I didn't realize it when I was recording the video, actually. So let's talk about rodent. Okay, and then when I get to the actual substance, I wouldn't mention rodent anymore, but I want to clarify the confusion. If you guys vaguely recall in rodent, right? Let's say in the machine, in rodent, in the machine, let's say I try to define some events. I would say event V, okay? Event E. And then I got some action. And for the action, let's say you got some begin, and also you got end, right? So if you guys remember, you can actually put a label besides every action, right? Action 1, action 2, action 3, right? Let me just say action 1 and action 2. Action 1, action 2. Put a label, and then you can do whatever you need to do over here. Right? There's something that we didn't really, maybe I mentioned that in the tutorial in 3342. Maybe I did. So that's an important thing too. We got two labels over here, label number 1 and label action number 2. Doesn't matter how many label actions you might have in a single event. Always, all the actions in a single event will be executed atomically. Have you guys taken a maybe database course before? Maybe many of you, right? Just in case you haven't, atomicity or execute something atomically simply means all the actions are going to be executed at the same time. There's no intermediate states, like a delay, okay? That's something very important for model checking. All right, so here in rodent, multiple label action always executed atomically. ATO atomically. Right? So this is some keyword we have to know. Okay, atomically. Okay, so just in case you cannot see that, right? ATOMICALY, atomically. All right. However, in TLA plus, very confusingly, if you got multiple labels, the updates are not going to be executed atomically. So that might be some errors you guys run into. So I actually that's the most commonly questioned during the office hour and also scheduled lab. All right, so that's why I want to clarify that as well. So just remember, in rodent, yes, that's the case, but we don't use rodent anymore in this course, right? So you want to just remember in TLA plus, it's not the case anymore, all right? And I'll give you a little bit more details about the relationship between the labels and actions and atomicity once I get to the concrete solution. So this is not the case for TLA plus. Well, it's just a different tool. So just the way they treat actions and also labels are just different, which is okay, right? So that's why whenever you want to move from one tool to another, always don't assume if you see a similar syntax, they really mean the same thing. Not necessarily in general. So this is a perfect example. Okay, I'll get there. And also number 3. So this will be a little bit more advanced, right? So also some of you also dropped by my office. I was asking, so you didn't really require us to really encode the system variance for the models, right? M0, M1, M2. Yes, you're not required because that one is kind of tricky to do. But it seems to me that maybe it's good to really show to you how you can encode it. It's not too bad. You just have to somehow, number one, we got to brush up about the variance. Let me show you what we need to do, right, for this one here. Encoding the variance. So what I would suggest is, now that we got to do it, we got to do it properly. We need to review, number one, about invariance versus variance. It would be very worth actually emphasizing again or reviewing again the difference. And then it would be nice to also review very quickly why we need variance. The reason that we need variance is we want to somehow measure or to prove that your system is lifelock free or divergence free, right? So these terms might still sound kind of rings the bell to you, right? So lifelock and also divergence, right? Okay, and also number 3, we got to talk about how we can, what will be the requirements on using the variance. There will be 2 criteria. The requirements on using variance. So there are 2 conditions actually. Do you guys remember which 2? Let's say I got some variant V. What will be the important 2 criteria for me to make sure if these 2 criteria actually are satisfied, then my system is lifelock free? Give me one. Okay, you give me the harder one. That's good. Okay, so I would say first one and second one. Right, the post states somehow I'll remind you guys should be less than the pre-state one. Okay, that's good. And by the way, that's only for new events, not for the old events, right? So that's why when I show you the example for M1, you do have to be careful about the encoding because only for new events you have to make sure this is the case. But for the old events, you don't need to. Right? Just be careful. All right? So this is only for the new events. What's the first one? The simpler one. Thank you. And the V here must be a natural number. Thank you so much. All right, so we got these 2. Right? We're going to see exactly how to encode these 2 into the Pascal, right? Just for completeness. All right, this one is very easy. You don't need to introduce any new variable. You just declare that as an invariant condition. And this one here, not that trivial. You will need to introduce some auxiliary variables to somehow know 2 things. Number one, am I in the post states after some new events or old events? You need to be able to tell, number one. Number 2, if I'm not in the context of the post states after some new events, now I should really somehow get this value here and this value over here, they don't have any default notation for you to use for the pre and post states for the tool. So you have to encode them explicitly. So that's something you will see. I'm going to show to you. Okay. So I have only encoded the variance for M1. So it will be you guys' exercise to encode the variance for M2. All right. So that will be some exercise worth doing. All right, guys, this is just a very quick walkthrough about a roadmap for what I'm going to talk about. I haven't talked about them yet, but in detail. But it's good to know the big picture first. All right, so let's now dive into the details for the first one. Right, let's talk about this one here. All right, this one here. And by the way, so I'm not going to go into the details about how you can do the while true and other things. That's something I would expect you to really go into detail. What I want to show you is the generated state diagram, to show you quickly about how you can see the points I'm trying to make about the loops or cycles. Okay, that's something I want to show to you. And use a little bit TLA plus from Remote Lab. All right, so okay, I'll also go to the TLA plus in a moment in Remote Lab. So this is the file you guys will have to look at. Okay, so this is part of the solution package, M0. I just make it very explicit, unbounded interleaving. Okay, so there's no restriction on the length of the trace. All right. I'm going to show you this diagram in just one moment, but let me just go to TLA plus. Okay, quickly. So the one I have already opened is called Bridge Controller M0 Unbounded Interleaving, right? So that's the one to look at. And I have already created a model over here, right? So you guys know about how to create a model. And one thing very quick, just to show to you. You can see that we do have while true over here as opposed to bound, right, over here. That's something you want to watch out right away, okay? And then for the model here, let me double click on that. Right, one thing to note. So now we don't have bound anymore. So the only thing we have to set is the D, right? Like a maximum number of cards, right? That can actually exist in the island. So this will be, just set it to be 1, just to begin with, right? I'm going to give you some quick summary about how things, some interesting statistics in just a moment. Okay. So this will be the one. Okay, D should be set to 1. And then you guys should really uncheck the deadlock, right? Like what you did in the tutorial video. And for the invariance, you can put everything inside, right? Invariance model 0, 1, 2, and deadlock free, right? Just put everything there. Okay. And then if you try to run it, I'll run it just once. Okay. All right, so one thing to note, right? Maybe that's something I didn't point out in the tutorial video. If you want to see how complex your system was, and also you can see the state graph here was generated. I kind of showed to you how you can generate it. You want to get yourself also familiar about this process here. It will be beneficial for you during the programming test. You will be able to get access to the tool like a dot tool to really generate a graph, but you got to know how to use it, how to set it up. Okay. One thing you can see here is this, right? You can see there's some statistics over here, especially here, about distinct states number. You can see at this point it's 12. Okay, what does that mean? That means when you actually look at the state graph over here, you will see 12 different circles there. That's about the 12 states we have. That's a very useful information. And I'm going to show to you very soon, just for you to also play with, as you adjust D to be higher, maybe from 1 to 2, 2 to 4, 4 to 8. Would you expect this number here to increase or decrease? Increase, right? You're getting closer and closer to state explosion. Not necessarily ultimately, but closer and closer. That's something I want to show you as well, right? So distinct states here, you want to make sure you also know how to look up this information, all right? All right, and then if I already run the checks, if I look at the state graph here, right? So that's a graph, okay, over here. You guys have seen that already in the tutorial video. Let me go over some detail with you very quickly, right? Just to highlight certain things. Well, the same graph, okay, over here, right? Not all the nodes I'm going to go over. You know what? Before the graph, let's see conceptually what this graph is really trying to convey, right? I'm going to draw something which is very similar to the counter example that we did kind of in week number 1 or 2, around that time. Very similar. That one there can really help you kind of understand roughly about what's happening in this graph over here. Of course, you guys will also need to dive into exact details into how things are happening here. The only difference I'm going to show to you will be you want to watch out how the PC value is being changed, right? We'll talk about the program counter, right? I can tell every time you kind of introduce more and more labels, you're going to get more and more possible PC value, like a program counter, right? That's very important. But now let's understand the stuff conceptually without any program counter, right? Just make sure. Okay, I'm going to draw some diagram here very quickly. Okay. So let's say we got, so the assumption is, let's say we got D is equal to 2, right? Just make it a little bit more interesting than just 1. Okay, 2. All right, so let's say we got our init, initial events. That one there is simply going to, okay, let me just get this one. That one is actually going to initialize all the values. So now we're talking about M0. So we don't have A, B, and C, just N. All right. So here I'm going to put D is equal to 2, constant, and also N is equal to 0. All right, like that. All right. And then we know that all the possible value that we should really have, it will be the N could be up to and including 2. So 0, 1, 2, like that. So this will be basically D will be equal to 1. Sorry, there's constant. And D is equal to 2. And N can be incremented to 1, and also N can be incremented to 2. And you can look at how we design the guards for MLL and MLN. They are designed in such a way that you just cannot go beyond this state to reach out another state where N will be incremented from 2 to 3, for example. Just not possible. Event is simply not enabled. We can also verify that in the actual generated state graph, which is something I want to show to you. All right, so here, remember increment, decrement, right? Exactly over here, right? So to go from N equal to 0 to 1 is going to be ML out, right? Assuming that you understand very well about ML out, all right? ML out. As soon as we reach this particular state, conceptually, this is already equal to that. The guards of ML out tells you that you cannot increment anymore if the value of N is not strictly less than 2. All right, something like that. So you should really now understand that conceptually, at this point over here, ML is simply not possible. It's disabled, basically. Disabled. Right? Let me just use orange over here. I'm going to show you the corresponding parts in the actual state graph so you can see the correspondence. All right? And also for ML out, let me just use blue here. ML out over here, and also ML out over here. All right, so we got 2 possible occurrences for ML because D is equal to 2. And also MLN is good, so you can see at this state here, this ML is enabled. Sorry, let me say it again. At this state here, ML is disabled. The only way to really make ML enable again is to have one occurrence of MLN to go back to this state, right? Because once you go back here, ML will be enabled for once more. All right, that's very important insight, which we'll also see in the state graph. So this one here is going to be MLN. Okay, MLN. I'm just going to show one. Of course, this one is here is also MLN, obviously. And I'm going to show you the correspondence just for this one here. All right, just for this one, the yellow one. Okay, I'll get there. All right, and then symmetrically, in the beginning states over here, it is not possible to reach out to any new states just by having MLN because it should be disabled, right? Just like how in this state, ML is disabled. So let me also do that one here quickly. So here, you know that here, MLN is also not possible because it's disabled. So this kind of corresponds to what I just said earlier about this model here basically is about using while true for selection. So we can select for as many events in the traces as we like, conceptually. But the resulting reachability graph here is definitely finite because you only got 1, 2, and 3 states. However, the number of paths for the system is infinite. Well, easy to see. Either you can say init, ML out, ML out, one path. Init, ML out, ML in, ML out, one path. Or init, ml out, ml in, ml out, ml out, ml in, ml out. You see what I mean, right? The number of possible paths from this finite graph over here is simply infinite. That's what model checking can do for you very efficiently. That's something we'll see when we get to temporal logic. All right. And one more thing to say, it is also important for you to know about pre-state and post-states. Okay. Let's talk about this particular ml out over here. At the starting point for this ml out, we know that n is equal to 0. So we call this the pre-states for ml out. Okay. N equal to 0 over here. That one there is the pre-states. Of ml out. And then after making that transition using the action of ml out, we're going to get n will be incremented from 0 to 1. So that one there is actually the post states of ml out. So far so good. But I want to draw your attention to another thing, right? I'm pretty sure you know as well. The same states may be treated as the pre-states for the next events, right? So this one here, you can think about this particular one. At the same time, it's going to be also the pre-state for the next ml out, all right? That's something we also see in the state graph. So this will be also the pre-states. So let's say first, second. And of course, this will be the first. Right? And finally, this will be, very quickly, this will be the post states of the second ml out. At the same time, the only way to make ml out enabled again, as we said, is to have ml in over here, right? So that one would be the pre-states for this particular ml in. So you want to really see very clearly about a pre and post state, right? It could be overlapping between the different events that might take. So this one here is also going to be the pre-states of ml in. Pre-states of ml in, which is going to enable ml out again. All right, so having these kind of a sketch at a conceptual level, let's now take a look at the graph, right, to see the correspondence, right? I'll try to be more consistent with the color, right? So you will see the correspondence. Let's now take a look at ml out, first of all, right? So these are the two occurrences we might have, okay? So I'm going to just go right to the point so you guys can see other details on your own. If you kind of get lost in the other details, you got to reach out to me, okay? ml out. And I want to focus on just about the action itself. So we're going to go to ml out action. This is one, all right? So guys, one thing important for you to know, you can see we got a program counter, right? So this, you can think about ml action is right in the beginning, right before we actually take the effects for the action. So think about this one here. It's like a pre-states. So that's why I'm going to put n equals 0 in green. So think about that's what I'm doing here. Pre-states and also ml action is corresponding to pre-states and ml action, right? That's what I'm doing here. All right, so that's the first one. And after that, you're going to get the post-states being n equals 1. And that one there, of course, correspond to n equals 1 over here as the post-states. Okay? And what about the second occurrence? For the second occurrence, I'm going to go there a little bit further. Well, of course, in between, there might be some choice, like a non-deterministic choice that's going to happen, right, to choose the events for execution. So we're going to do another ml action here, right, over here. So that'll be a second one. So this one is going to correspond to just the second one over here, okay? And for that one there, let's use a consistent color here. ml action over here. And also you can see now the pre-states is actually n equals 1, and the post-states is n equals 2. Well, it is very important as soon as we get to the post-states, right? Let's be very clear. So that's the first ml out. That's the second ml out. At the post-states of the second ml out, according to the conceptual sketch, we know that it should be disabled. Let's see, okay, sorry. There we go. So let's now do some very quick annotation here. And this post states of the second ML out. It is disabled, right? Because of the value of n, we are reaching the maximum, like d equals 2. How do we see that it's disabled, right? You will see that you will not be able to actually do any more ML out action anymore, according to the graph. So you can give a try. So, but what you can do at best, right? I'm going to show you in the orange, right? Remember, we use the orange to show the disable, right? Let me use the orange here, okay? So let's say after this post states over here, so what we'll do is, I'm going to use orange. We're going to go back to the choice over here. You can see now the choice, the non-deterministic choice. Let's say the non-deterministic choice happened to choose ML out again. However, this ML out here is not about the action itself. You just say it's chosen. The action will be called only if the ML out is enabled. But some will not be able to. You can see it just go directly back to the loop itself. So that means you never get a chance to have any ML out action until you do something else. Right? It is important here. That's how you see the correspondence. Okay, so this part over here, what you really want to convince yourself is no more ML out action. Until n value is decremented from, at the moment it's 2, right? 2 to 1, which can only be achieved by MLN. All right. So it is important to see this part over here is really about the disable, right? ML being disabled. All right. Let's now take a look at the final bits. How can we show this particular one here? So given that this state here is always about disabling ML out, which is good, but now how can we get this ML in? How can we get that, right? To see that one there, okay? So you're going to follow this path here. So let me first of all highlight to you. ML in action is actually here, right at the bottom here. Okay, ML in action. At the point that you're trying to do ML in action, n is equal to 2 in its pre-states. I'll show you that. You can see this particular transition here, the pre-state is when n is equal to 2. The post-state is n is equal to 1. Okay? How do we see that in the diagram? So what we'll do is, you can see that once we chose the MLN for execution, and so we go ahead for the MLN action because it's enabled. So what it will do is, it's actually going to go all the way up. All right? Follow this arrow over here. It's going to go all the way over here. And then you can see that the post state is now n equals 1 again. Right? That's exactly what we go from this one here to n equal to 1. And now at this state, ML is enabled again. That's a cycle. Exactly, right? All right. All right, final point here. So this is about a cycle. Going back to an existing states. We are not reaching out to any new states, right? The graph is finite by having cycles. And existing states where ML out is enabled. Right? It is very important. Right? Because once you can see once you get to this state here, you can see if you follow through, there is a possibility to select for ML action. Right? So it is enabled. All right, guys, any questions so far about this point number 1? All right, point number 1 is about what should you review about point number 1? Number 1, you should really go back to TLA plus, the solution, right? you want to go back to the module itself and really make sure you understand about the while true, compare that with the while bound less than while I less than bound, something like that. That's number one. And number two, you're actually going to look at this state graph that's generated and try to convince yourself how the circles and also edges kind of make sense, right, about the different scenario, which I kind of showed to you, right, about the correspondence. Final thing, and we can move on to point number two. And this will be some interesting statistics to share. Okay, I'll write down the summary, but let's now take a look at here. If you look at the model itself, okay, if you go back to model overview, at the moment I got D equals 1. So what I want you to try is you can just edit the same model. You don't need to create a new one. For example, you can change this one here. Also, every time you want to do it, just increase that to be maybe double the times about the D, double the value for D. Maybe from 1 to 2, 2 to 4, 4 to 8, and etc. Right? I'm going to give you some summary here about the statistics, okay, for this one here. So if you think about the value for D, I'll make it thicker. The value for D and also the number of distinct states. Distinct states will just be about how many circles you have in the graph that's generated. Distinct states, right? So these are the two things, right? So when it is equal to 1, it will be 12. When it is equal to 20. And the one we are currently looking at, about 20, right? Very quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 20, all right? And then if D is equal to 3, it's going to be 28. 4 is going to be, I'll just give you a few more. 36, 5, 44. So on. If I get 8, for example, that will be 68. So what you should really notice the pattern is something like this, right? That's whenever you want to, let's say you're using TLA plus to really convince your supervisor, about the verification or how much confidence you should really have about the verification result. When D is equal to 1, we are considering 12 different states. Double the D value, it will be 20. And then double it again to 4, you got 36. And then you got 68. So roughly speaking, you can see 2 times, 12 to 20, roughly 2 times. And 20 to 36, also roughly 2 times. 36 to 68, also roughly 2 times. That means every time you double the value for the D, the maximum bound, about number of parts in the island, you're going to double the number of states. Right? That's about the linear growth, about the number of states. For this particular example, it may not be too bad, may not be. Okay. All right, any question about highlight number 1 from your Lab 1 solution? John, question?
Yeah, so when we do like MLN, when PCs at MLN or MLL, that's the event guard being checked, right?
Okay, about the PC, right? Yeah, let me show you. So for example here, you can see the loop is just about we are about to make some selection. And choice is about where the non-deterministic choice is just about to happen. So let's say here, if MLL happen to be chosen, which is okay. At this point here, we are not really checking to see whether the guard the guard is true or not. No, not this point. I'll show you why. Okay. If you go back to, let's say, the model here, right? You can think about the choice over here is right before we do the either or. Okay, and then when we get to MLL, it's right before we check the guard. So guard is only checked after the PC is set to MLL, basically. Okay. Yeah, transition after. Okay, let me go there again. That could be something just to repeat one more time. So let's say if we got MLL over here, that means somehow MLL is chosen. Chosen doesn't really mean it's going to be executed. If its guard is enabled, then we'll execute it. So now when we get there, we just go back directly to the loop. Because at this point here, when we try to check for its guard, it's simply false. So we don't even get to its action. On the other hand, if you look at some cases where it is enabled, let's look at this one here. Okay, you can see we got choice, and then we got MLL is chosen. And then, so at this stage here, we're going to evaluate its guard. it is enabled. So we can call that. And once we call that, we're going to execute its action. And then we get to this particular state. Okay? So we really want to kind of compare the case where an event is actually enabled versus disabled, right? There will be some intermediate details that we have to work out, as opposed to we only look at like a simple state like this. This is only for conceptual sketch. Yeah. Question?
Professor, in this case, it's linearly increasing with D and the distinct states. But let's say we have another example where with one trigger there are a few more events being enabled. So it just goes up.
It definitely goes up. Yeah, so I would say this might be the simplest scenario we might have for model checking. As you said, we only got two possible events, ML in, ML out, like a counter example, increment or decrements. And also, every state, you either got increment or decrement. So the way they actually grow is kind of like a linear, like a multiply by 2. But as we get to more complicated example, you may have some sequence, you may have maybe some tuple, you may have maybe 5 different events that might be available for execution. So definitely will increase the complexity.
So how do we trace such events if there are multiple events being triggered at the same time?
Of course, I would say what you normally do is like this. Okay, I'll just get to it. What you normally do, I would say, okay, let me say this. Okay, so now, important practical advice for you. All right, when should you really look at a state graph, right? Of course, you guys should always make sure you define your module as correct as possible at the first go. Wow, that's ideal. Okay, number one, when defining your modules, try to be as correct as possible. This is pretty much saying whenever you're writing Java code, right, or writing any code for implementation, you want the implementation to be as correct as possible. Similar idea, right? We hope. Okay, but number two, very crucial. Also crucial for your lab number 2. Write good invariance. Or in lab number 2, we're going to show you something called assertions. To verify the correctness. All right, now from number 2 over here, you got basically 2 results. Let's say your model checking is going to terminate, so we don't have like a out of memory option there, right? Either the model checker will say yes, you got everything good, or you may say no, you got some counter example, right? You got 2 possibilities here. The TLC checker say yes. In that way, you can leave it like that. That's one way. Or if you want to be double check, just to make sure maybe everything is really working well, I would suggest you choose some very small constant value and generate a state graph accordingly. And look at the state graph and try to convince yourself that's really how things are supposed to work. Maybe somehow you have defined your module in a way that the state graph simply doesn't work as expected, but somehow the property just happened to pass. That's not good. It's more like it's like a false hope for you, really, about being correct. Okay? So this one, I would suggest set small bounds on constants. And inspect the state graph or reachability graph to make sure the system works as expected. Okay, I would say this one, even though it's more like an optional, but it's highly recommended. You want to make sure you didn't simply define the wrong system, but somehow the wrong system passed the property that's not as strong. All right. When I say property being strong or weak, that's something you guys will experience also in lab number 2. I'll talk about it when I get there. Okay. All right. So that's the case where TLC checker will just give you a green check. That's great. On the other hand, more likely than not, the TLC checker might just say no. Right? It's going to give you some error trace, 1. Of course, error trace, which will be point number 2 I want to make when I get there. Error trace is something you also want to study. So this will be, you have no option. This will be mandatory. You have to look at the state graph and look at the error trace to see what's wrong. Okay? Need to study this, the error trace, with the reachability graph or the state graph together. You have no way around. And from there, you got to work out the fix. The fix could be you found that maybe there is some transition that should be enabled but was actually not enabled. Or there's some transition that should be disabled but it was actually enabled, right? Things like that. So you may have to fix the guards for the events. Okay. Okay, so let me just write down what I just said, right? So you can also take that as advice. So, for example, there might be some event E, maybe should be enabled, but not the case on the graph, right? Or it should be disabled, but not the case in the graph, right? You got to look at those kind of weird cases and try to fix it. Pretty much like when your JUnit test case failed, what would you do? You basically step into the assertion and try to look at the debugger, right? And then try to work out things. Just the same debugging process. It's just that now we are not really debugging code. We're debugging design model, right? But the principle is really the same. Okay, that kind of answer your question, I hope? Good, very good. All right, guys, any other follow-up question to point number 1? Okay. All right, so now we just finished discussing just point number 1, just about reachability graph being finite, right? I got 23 minutes. Why don't I talk about this one as well, quickly, right? Hopefully 10 minutes, and then we'll take a short break before we talk about the variance. I can potentially maybe only talk about this one here. I can save this for next time. I do want to save some time to talk about lab number 2. I think that's important, okay? Let me talk this one a little bit. I can leave at least 10 minutes today for lab number 2, and whatever that's left, I'll finish that maybe on Thursday, okay? Let's talk about atomic versus non-atomic updates, which is important for sure. All right, for point number 2, all right? Let's say we talk about this model here, right? So if you want to reproduce what I'm going to show to you, it will be bridge controller M1, no variance, right? So that's the model TLA module that we're going to look at, right? Okay, I'm going to go right to the point. I want you guys to look at these 2 versions. So I got my bridge controller M1, that's the algorithm, and also bridge controller M1. For both of them, we got NABC, NABC. And for ML out only. Well, of course, you can try to maybe create similar error, maybe for MLN. You can do that as a practice. Okay, I'm going to show you on the tool as well, just to convince you. But before that, I want you to compare these 2 procedures very carefully. Okay, they're basically trying to do the same updates. But what difference do you see between these 2 algorithms? Eh?
Multiple labels.
Yeah, exactly, right? That's the point, right? You can even see from the title here, multiple versus single, right? Just to make sure, okay? So here, for version number 1, you basically got, in some way, I kind of use the name of your fellow student when they came to my office hour. Hope they wouldn't mind, okay? So here we're updating N, which is an abstract variable. So I say ML out action abstract. Versus when I'm updating A, that will be the concrete variable, right? I got 2 labels. If you're thinking more like a rodent way, having labels, label action, they will be executed atomically. No, that's not the case, right? So we're going to correct your understanding for this course, right? And on the other hand, you can see now all these are considered as under one single label. All right, that's something I would like to talk about. Okay. Before that, let me just show to you why one version will work, but the other one wouldn't work. For those of you who actually just got this solution at the first go, maybe you never realized this might be an error, right? For those of you who tried this one first, that's how you run into the error. Right? Let me show it to you. Okay. So if you, let's go back here and let's now open, let's say M1, no variance. Okay. Let me also close the other M0. Okay, so this is the one. Okay, you can see here, I'm showing to you the single label version for this guy here, right? Single label, ML action. I shouldn't call it abstract, maybe just ML action, right? That might be a little bit better. But guys, remember, every time you modify the algorithm itself, you should translate, right? That's something I kept emphasizing in the video. I'm gonna say file, and then translate. Okay, all good. And then I'm gonna go for model here. All right, you can see uncheck that lock, and also I got auto invariant here. All right, this one works, right? You can see there's no error trace. And for D is only 32 states because I chose a very small value for D, but good enough for their demonstration. On the other hand, let's now try the multiple label version to convince you, okay? ML action here, I would say abstract. And over here, I'm going to say ML out action concrete. Oops, sorry. All right, save it. And I got to retranslate, just don't forget. File, and then translate. Okay, nothing wrong. And I'm just going to double click on the model again, and then run it. Aha, right? You can see now, right? If I introduce an extra label, that's where the error is going to occur. So let's say this. Maybe during the programming test, you were trying to encode, check some assertion, and then you found that you actually didn't check certain property. So that will be the only information you will get, which is important. Of course, you got to make sure, I didn't do that for the, oh, actually, I also did that. You can see you got error trace over here. You also got state graph over here. So these are the two things you should really look at in parallel. Right? You got to look at the graph, and also got to look at the trace. And the trace is something you can look into detail, but I will show you exactly on the screenshot. Okay? Anyway, so we got two versions over here. Okay, so let's now talk about them very quickly. What's really happening here is as follows. Before that, so this is, think about this action here and this action here. They will be executed, one followed the other. Okay? So this action number one, executed atomically itself. And also action number two, also executed atomically itself. But the problem is, you can think about there will be some certain gap in between the execution for the two events. And that gap is where the invariant violation can occur. That's also what the error trace is going to show to you. That's something I'm going to point out to you as well. Okay. On the other hand, if you only got a single label over here, what's going to happen is these two actions over here will be executed together atomically, right? A single label. Action 1 and action 2 executed atomically. And this is the version you want to keep, right? Got to watch out for that. Of course, you also got to understand, if I give you some version like this, let's say on some test context, you also need to know, spot that first and then fix it, or even to explain to me why it doesn't work. All right, that's important. Let me do a little bit conceptual sketch, and then I'll move on to this state graph. Just point out to you, okay, quickly. Okay, so let's now do this one here. So I got init. Let me talk about this version here, right? Just this one. Let's see why this version is wrong. And then I'll actually show you the other graph that's actually right. So init. Oh, by the way, the invariant that we want to maintain is this one here, right? A, B, and C should be equal to n, right? What's going to happen is if I try this, let's say in the init states, because we know that initial states, the ml out is simply enabled. We know that pretty well, right? In the beginning, let's say n will be 0, A, B, and C are all 0, all of them. And then what's going to happen is like this. This action 1 is going to be executed first and resulting in some post states. Okay? So what's going to happen is we're going to get another, okay, let me just save some writing here. Okay, and then I'm just going to wipe out the values and we're going to fill it in. So the only thing that's going to be executed will be this guy here, right? We're going to increment n. And that one there, let me just call that abstract, but you know what I mean. So this one here will just be action abstract. That one there is only going to increment n. So that means n is going to be incremented from 0 to 1, whereas all the other values are just the same. Notice one thing here that's very important. This state here does not contain any resulting updates from the second action, which is important to make sure the invariant will be preserved, but it's not. So now, as soon as we get to this particular state, right? We have to understand that over here, this particular state over here, this is where the model checker is going to complain to you and generate an error trace. So this one here, invariance 1, 4 is violated because you can see n will be 1. 1 equals 0 plus 0 plus 0 is simply false. Right? That's obvious to see. And conceptually, you might be thinking, I'm really waiting for maybe another concrete action to really happen. I'm waiting. So maybe action, maybe concrete, right? So that's like the second one here. You might be thinking, right? And that one there, presumably, is actually going to fix the problem. And that one there is actually going to, so here we got n here and a here, right? So n remains to be 1, but we're going to increment a by 1. So 1 here. So here you can see 1 equals 1 plus 0 plus 0. That one is okay. But the problem is violation already occurred. The tool doesn't care. As soon as you reach this state here where invariant number 4 is violated, the tool will simply stop here without even considering the second updates. That's something important for you to see. All right? I'm going to write down here. It is very important for you to see this, right? I'm going to draw a very solid boundary over here. At this point here, the model checker is going to stop and generate the error trace accordingly. It's not even going to consider executing action concrete because the violation already occurred. All right? So think about this state here is really a bad state, which I'm going to write in red. Okay? So the model checker, the model checking stops at this state to generates errors trace. Right? It does not even go here. Okay? That's important. Okay? I think I will, for this, as far as discussing lab number 1 is concerned, I'll pause over here. I'll resume from this point here from Thursday. Right? I want to leave just enough time. Take a short break, and then we can talk about lab number 2 very quickly. Right? I think that's also important. Any questions so far? Huh? Sorry? Never mind. All right, sure. Yeah, so let's now maybe take attendance. Maybe that's what you were wondering about. Okay, maybe we should take attendance and take a short break. After that, we'll talk about lab 2. But for this discussion here, we're going to come back. Guys, these are all good stuff. You should really try to follow the point. Well, if not, study them, right? They will come back. All right, for Lab 1 discussion, I'm going to resume from that point there on Thursday. But for now, let's talk about Lab 2. All right. All right, officially it's released just as of today. All right, so you got about slightly less than 2 weeks, February 6th. Right? And on that particular day, I will also schedule your mock-up test for programming test 1. I'll give you more details later. Okay? All right, just make sure don't miss the deadline. Do your best before that deadline. And then important to take a look at looking ahead, right? So for your lab number 1 and 2, they both are relevant to what you're going to do on programming test 1. I do beg your pardon. I'm going to fix this, not March 7th. Not that case. I'm going to fix that, okay? And then lab 1, basically you can take a look. That's basically what you did. You kind of learned about the basic syntax for Pascal and also about all the various different usages of the tool. That's something we expect you to do during the test. Now, lab number 2 is very important. Okay, let's now take a look. Lab number 2, which you're going to complete. Of course, you still want to explore Pascal syntax, but this time you're going to get more. You have to look into conditionals, if then else, loops, not just the simple while loop that how we use, but you still got to use a while loop, but going to use that for more like an algorithm, like back in maybe 1021, 2030, and 2011 data structure about the complexity, right? That's what you got to do. No recursion, by the way, just an iterative algorithm. And also tuples. And think about the tuples over here, it's like a list, right? That's also you will see. Well, what you're going to be required to do is to implement some sequential algorithm, basically a piece of code, right? Execute it from line 1 to line all the way to the last line. Implementation of some sequential algorithm. And then the second part here is important, the highlight. You got to write some Boolean expression that will be checked as assertions. That's something I will give you some guidance today, but I can talk a little bit more later when we go over the solution for lab number 2 later. Okay. Basically, the assertion that you're going to write, they will not be like an invariant. Think about invariant as something that should be true at the post stage for every event. But now, if you talk about the assertion here, they only need to be true for certain events. That's what we call post condition. Right? You guys heard about post condition. Maybe from 3311, when you did a software design, post condition. So this will be the emphasis for lab number 2. And you'll definitely be asked questions about write your own post condition for programming test 1. So lab number 2 will be your best chance to practice. Okay. Okay, and then let's see. Okay, so workspace, that's fine. Resources, again, this document here is going to be made available to you during the lab test. And then the background. Okay, so you guys can definitely read it, but I just want to highlight certain terms, right? You can read it and then let me know if you got any confusion. But I think it's very self-contained. You got to watch out for, I got 5 minutes, you got to watch out for post condition, right, for sure. And also precondition, thinking this way. In Pascal, you're actually going to specify some algorithm, right? Some algorithm in the Pascal syntax. There might be some assertion you have to check beforehand to make sure all the inputs satisfy the expected condition. Assert something. So this will be the so-called precondition. There could be multiple assertions, by the way, for the precondition, for sure, right? There could be. And also, we got at the end of the algorithm, upon its termination, we may also want to assert certain Boolean predicate here, and that will be the so-called post condition, right? Your lab number 2 and also your programming test, most likely 1 and 2, both tests. You will be asked to, number 1, to implement the algorithm in Pascal syntax. And then you have to specify the appropriate precondition and postcondition. Right? So that's a big picture. Okay. And of course, you can think about the assertion, they will be checked using the TLC model checker. And then when your assertion don't really pass, what should you do? Well, you should generate a state graph and look at the error trace carefully to debug, right? That's the way to do it. Okay. All right, so what about the task? Task number 1 is really there just to really get yourself going. Of course, you can simply just highlight and just copy and paste. I would suggest not to just copy the text over here to paste to TLA plus. It might be better to your benefits to really study the basic syntax over here carefully. We have chosen some very representative syntax you might have to use for the test. Not all of them, but at least some. I would suggest really try to type exactly these characters one by one into your by creating a module and type them into the Pascal algorithm. And then you can see we got, let's say here, let's say for this one here. You can see we got assert. So that one there is one example of post condition, right? That post condition here is rather straightforward. That one there does not involve any logical quantification, but there will be something you have to write for sure. That just get you started with. Right, you gotta just type in and then make sure everything verifies before you move on to the next one. The next one there is just another one. That one there, we do have some post condition. You can see that one uses universal quantification. Right? You can see /A, right? That's a universal quantification. And also you got some precondition over here. That's also assert, right? So study these two examples very carefully and then type it out into your remote lab, and then these files should be submitted. Okay, so that one should really give you a very good starting point for the actual task. That's task number 1, 2 subtasks. And then task number 2, right? You can read the instruction here, but you're actually going to do 1, 2, and also 3 tasks over here, right? For each one of them, you can focus on, first of all, get the algorithm part right. Just get the implementation as correct as possible. And then I deliberately did not give you much hints about exactly what precondition and postcondition you should really write. Before the submission deadline, I would suggest you guys can collaborate, that's okay, or think very hard about if you want to specify some postcondition, let's say, to really specify what should be the relationship between the input and the in the result, like output. You want to really write as complete as possible for the predicates. I want to challenge you about how complete your post condition can be. If you're very happy, if you're very confident about the completeness of your post condition, come to my office hour. Most likely, I can challenge you and tell you that you haven't caught, for example, a certain scenario. Of course, you could have done it perfectly as well. Okay, 1 minute, and then I'll let you go, please. Right, so, and then in the actual solution for these 3, especially for the last one, or maybe the last 2, I'm gonna give you some very interesting, it's necessary, but kind of sophisticated post condition, which I'm gonna go over with you. You can expect that kind of difficulty in the actual test. All right, so just to give you a little bit motivation. All right, and then submission, just the same before. All right, so that's about lab number 2. Start working on that early. It's due actually next week. And then if you got any trouble, let me know. All right, thank you. I'll see you on Thursday.